Hello, today is Thursday, April 29th, 2021, and I'm recording this presentation. It's the keynote address I will be giving at the IEEE Big Data Security Conference, and that's going to be on May 15th, around May 15th, 2021. And I usually record the presentation ahead of time in case there is a technology glitch. And so I'm Bhavani Thuraisingam from the University of Texas at Dallas. And I'm looking forward to recording this presentation. So I'm going to share the screen. Okay, so the title of my talk is Integrating Cybersecurity and Artificial Intelligence with Applications in Internet of Transportation and Infrastructures. And again, it's recorded on April 29th, 2021, and the keynote address to be given on May 15th, 2021 at IEEE Big Data Security Conference. So, the outline of my presentation, 3 parts. First part is integrating cybersecurity and AI/data science. So I use the word AI, machine learning, data science interchangeably. And just one second, just want to make sure, yes, that the sound, right. And so the topics I'll be discussing: big data security and privacy, and then privacy aware quantified self. And first I will talk about data science ML AI for cybersecurity. So it's called now AI for cybersecurity. And then I'll talk about securing the data science machine learning AI techniques, because these AI techniques or machine learning techniques could be attacked. And so I'll be talking about that. And then finally, I will discuss trustworthy machine learning, artificial intelligence. And then part 2 is on security and privacy for Internet of Transportation and Infrastructures. And part 3 will apply part 1 to part 2. And so that's applications of SecAI, security and AI for Internet of Transportation and Infrastructures. Okay, so we have a number of sponsors, as I've said, NSF, ARO, Air Force, NASA, NIST, NSA, and so on. And it's a team effort. And I thank my colleagues, Professor Alvaro Cardenas, Professor Murad Kantajulu, Professor Latifa student, and Latifa Khan, and our former student, PhD student, Dr. Raul Quinones, and our project coordinator, Ms. Rhonda Walls. Okay, so part 1, integrating cybersecurity and AI machine learning data science. So what is the motivation, right? So data mining, security, and privacy. So I introduced the idea back in 1996 at the IFIP 11.3 conference. So it was on data mining, security, privacy. And I talked about the privacy violations that could occur due to data mining. And later at the Pacific Asia Knowledge Discovery in Database Conference in 1998, and subsequently published what I call a landmark paper. I'll explain to you why. While I was at NSF in 2002, that spawned a new area of research. So why do I call it landmark paper? Because when you're a program director at NSF and when you publish a paper, especially providing directions, of course, everyone pays attention because you have the funding, right? You can fund various efforts. And so I also gave this same keynote address at Pacific Asia Knowledge Discovery. That was in 1998 in Melbourne, Australia. And the IFIP was in Como, Italy. So privacy preserving data mining, you have the original data, you add some noise. So X prime is the noise added to X. And then you have a modified data mining process, but the end result, so you need to have the original, you have to reconstruct the original distribution. And then the final modified result, right? The final result should be the same because, or similar, because you don't want the data mining or machine learning to find something completely different. So then I joined the University of Texas, Dallas in October 2004, and our research with PhD student Dr. Li Liu focused on privacy preserving decision trees and the perturbation method between 2005 and 2008. So data mining security and privacy is exacerbated with big data and data science, and I hosted an NSF workshop on big data security and privacy in September 2014 and presented the results to the interagency working group in February 2015. Okay, so what did we do at the workshop, or what were the findings, right? Big data management, security, and privacy. Due to the technological advances and novel applications, it is now possible to capture, process, analyze large amounts of data. And these are for a variety of tasks, including security tasks. So such tasks include user authentication, access control, anomaly detection, user monitoring, protection from insider threat. And so by analyzing all of this data, right, you can collect it on the web or otherwise, you can identify connections and relationships among individuals. And this may in turn help with homeland protection, disease outbreaks like COVID-19 and so on. But this collected data, even if you anonymize it, say by removing identifiers, you can put records together and link these records, and you could re-identify the individuals, right? That's the challenge. And so this information, if misused or stolen, right, can lead to privacy breaches. And so machine learning, big data analytics techniques also could be attacked. So on the one hand, you need machine learning for cybersecurity applications like insider threat and so on, but the machine learning techniques themselves could be attacked. So the directions we said, access control models, and so this is access control for massive amounts of heterogeneous data, and then privacy enhanced techniques, big data for cybersecurity, and secure machine learning. Okay, so I'm not going to talk about the first area, access control models for big data, but I'll be touching on the next three topics: privacy enhanced techniques, big data analytics or data mining or machine learning for cybersecurity, and then secure machine learning. Okay, so privacy aware quantified self. This is an activity that social scientists and psychologists, they started the quantified self movement, because it's really great because you collect all types of information about you and you analyze the information, and it can give you some advice, right? Healthcare advice and so on. Like for instance, I really like vanilla ice cream and milk chocolates. So when I open the refrigerator, by the way, I don't have any of it in my refrigerator, right? So, but assume that I have. And if I open the refrigerator and go to eat milk chocolates and vanilla ice cream, wouldn't it be great if my iPhone or even the refrigerator would tell me, no, you're not supposed to eat that, right? So that's what the quantified self movement is all about. And so let's lot of personal data can be collected by wearable devices and smartphone applications being analyzed to give guidance to users in improving their health or personal life habits. These data are being shared with other service providers, retailers, using cloud-centric, cloud-based services, bringing potential benefits to users. So such data collection and sharing are often being carried out without the user's knowledge, bringing grave danger that personal data may be used for improper purposes, right? You can see all the Fitbit, and here you have your glucose collection, glucose monitoring, and what happens if it goes to the wrong hands. For example, data collected by device monitoring blood glucose levels might be used by insurance company to deny coverage to a user and even to a user's blood relatives. So suppose, fortunately, I don't have diabetes, but let's assume I have. And then if that information goes to the wrong hands, my son and might be, denied coverage, right? So, one has to be really careful. So such privacy violations could easily get out of control if data collectors could aggregate financial, health-related tweets and Facebook activity and all kinds of stuff. And then sell it to others. Data collectors could sell that information. So your privacy could be violated. This could result in lawsuits against data collectors and psychological and physical. It could also cause psychological and physical distress. To address these growing challenges, we need not just quantified self, right? That's what the sociologists and psychologists are doing, privacy-aware quantified self. So we need tools for privacy protection in quantified self applications. So what do we mean by that? So we have health-related fitness data, location data, social media, image, all of the data being collected by our smartphone, right? And then some of the data could be sent to the cloud and accessed through cloud-based services. Some of the data could be encrypted. What we are developing is this piece here, privacy-aware quantified self-manager. So for data collection, data storage, data analytics, data sharing. And what we are saying that policies should drive each of these functions. Policy-aware data collection, policy-aware data storage, policy-aware data analytics, and policy-aware data sharing. So policy-aware data collection, storage, access, analytics, learning, and sharing, right? So this is what we are building. And some of the data, of course, goes into the cloud-based encrypted data store. So as more data being collected, the storage on the device will not be sufficient to store all of the data. We envision an encrypted cloud storage component. All the data and less frequently accessed data could be pushed to the cloud. And again, access control policies will have to determine, right? Policy aware. So local apps running on the device will be given access to some of the collected data. When needed, these apps will be allowed to access some of the encrypted data stored in the cloud via a simple query interface. And in some cases, the data may not be needed in fine-grained form any longer, right? Example, storing 20-year-old daily weight data may not be necessary. Instead, storing and mining monthly average weight data could be sufficient for supporting various medical applications, right? So for a 20-year-old person, you don't really need to weigh that person every day, especially if the person is quite healthy, right? But for a 70-year-old person, it might be a different situation. In other cases, the data may have to be deleted to preserve privacy, right? So the whole challenge is when you delete the data, right? Is the data really deleted? You've got to audit. So example, delete and or generate fake location data to hide the fact that person participated in a protest. But deleting is a problem, right? We have to make sure that data is indeed deleted. We envision that data sharing and analytics will be carried out using the services running in the cloud. And again, based on different scenarios, some of the data could be sent without modifications like heart rate for medical diagnosis, and some will be sent after sanitization, randomized response-based techniques to hide users' true response, and some will be sent in an encrypted format that will enable the distributed computation of extracted data mining results as needed. Okay, so again, the key point here is that the policies are guiding data collection, data storage, data access, and analytics, learning, and sharing. Okay, so now we go to the second topic, data science, machine learning for cybersecurity applications. And it's joint work with my colleague, Professor Latifa Khan. And it's actually, this is a third topic, right? Big data security, privacy, privacy-aware quantified self, and data science for cybersecurity. And we are looking at massive amounts of data. So data streams, data continuously arriving, right? So data streams, continuous flow of data, very common in our connected digital world, have massive amounts of data. And so the whole idea, you might think it's very simple. Use past data to build classification model, predict the labels of future instances using the model, and helps with decision making. So you have, say, lots and lots of network traffic continuously arriving, and then you build classification model, benign, and then you have that's for the training. Then testing, if it's benign, you just sort of store it in the server. If it's malicious, attack traffic, you block and quarantine. So what is the research? The research, because we're talking about big data, massive amounts of data continuously arriving, the concepts are going to change. Today, we will say buy Microsoft stock. Tomorrow, it could be Apple. The next day, Google. The next day, Amazon, right? And so every day it's going to be, and the next day, Facebook. Every day it's going to be different. So concepts are changing. One model may not be sufficient because its data is continuously arriving. So what do? We will have to update the model using human in the loop, or we also have an algorithm for model update. And so essentially what we are doing is real-time machine learning. And one thing we are doing for the model updates is that we throw away the models that are no longer valid and then replace it with new models. So we are building essentially what we call an ensemble of models, right? So we have this very nice algorithm and the technique for model updates, building a collection of ensemble. We applied it for a variety of application, including insider threat. So what is insider threat? Bad people behaving, pretending to be good people. So this could be humans, but we are looking at bad processes. And if you really look at the bad processes, it could be like it could look like a very legitimate process, like a database process or some application process. So insider threat detection requires the identification of rare anomalies in contexts where evolving behaviors tend to mask such anomalies. Because remember, it's continuously evolving. Data is evolving. So we have designed and developed the ensemble-based stream mining algorithm based on supervised learning that addresses this challenge by maintaining an evolving collection of multiple models to classify dynamic data streams of unbounded length. Okay, so the result, we use supervised learning, right? Support vector machine, in particular, traditional as well as one-class support vector machine. And we also looked at unsupervised learning, right? So their ensemble-based learning algorithm that maintains a compressed dictionary. We collect all of these words, compress them because we have millions and millions and millions of words. We cannot look at all of them. So we compress them like repetitive sequences found throughout dynamic data streams of unbounded length to identify the anomalies. In unsupervised learning, compression-based techniques are used to model common behavior sequences, right? Behavior of these processes. This results in a classifier exhibiting a substantial increase in classification accuracy for data streams containing insider threat anomalies. This ensemble of classifiers allows the unsupervised approach to outperform traditional static learning approaches and boost the effectiveness over supervised learning approaches. Okay, so here is our picture. So we have collect all of the sequence of words like system calls and so on. So you have I chunks we are using to train, gather data from chunk I, combine it with the previous chunks, extract features. And then our learning algorithms are support vector machine, one class support vector machine, and GBAD, unsupervised graph-based anomaly detection. And then we develop an ensemble of models, ensemble-based stream analytics. And then, right, so that's when ith chunk arrives. So then the model updates, right? All models are thrown away, outdated models. Then when the I+1 chunk arrives, we extract features and then we do testing. Is it anomaly or not? So again, it seems quite straightforward, but the challenge is to extract the right features. That's not an easy task. And we need security expertise and developing this ensemble of models. Okay, so, right. So that was, and we have applied our techniques for a number of applications, email worm detection, botnet detection, and so on. So I'm just giving you a snapshot of one particular application. Okay, so now we move on to machine learning techniques being attacked, right? Because everywhere we turn, machine learning is being used, whether it's for COVID-19. In fact, recently I read a paper from Mayo Clinic where AI algorithms are detecting atrial fibrillation, right, AF, better than just the other traditional techniques, right? AI techniques are much better now in detecting cancer. So without a doubt, healthcare, finance, everywhere with deep learning, right? So AI is something that's, it's being used everywhere. But imagine if these AI techniques are attacked, right? So the adversary is constantly looking at our behavior and trying to thwart our data, modifies data to defeat the learning algorithms. And so we have to understand what adversarial learning, what is the adversary learning about us? So it's not concept drift, it's not online learning. Adversary adapts to avoid being detected during training time, data poisoning, during testing time, modifying features when data mining is deployed. So there is game being played between us, right? And so that's a data miner, machine learning experts, and the adversary. So look what happens. This is the support vector machine boundary. The red squares are bad instances and the blue circles are good instances. So adversary is watching and learning. And then what it's trying to do is to push all the bad instances right below this boundary line. So it's pretending to be good instances. And so we have to then figure out what is the adversary doing. So it becomes a gameplay. There's a lot of mathematics involved, right? So what is our solution? Before I talk about the solution, we've got to figure out what the attack is. What is the adversarial attack model? So we looked at two types of attacks, free range attack and targeted attack. And we published it in our KDD paper around 8 years ago. Adversary can move malicious data anywhere in the domain, right? So the malicious data, there's a lower bound and an upper bound for every J. So I won't go into the math, the paper describes everything. And then the targeted attack, right, is adversary can move malicious data closer to the target point. So the challenge here, remember, we are only looking at two classes of attacks. And that itself is tough. In the real world, there could be hundreds of attacks, right? So how do we handle all of them? So let's look at our free range attack. So what do? First of all, so adversarial support vector machine, right? We are developing our support vector machine, adapting it to combat the adversary. Our threat model, test time, deployment time attacks. Attacker modifies X to X prime, modify packet length by adding dummy bytes, add good word to spam email, add noise to an image. So this is our original support vector machine boundary. Okay, so black dashed line is a standard support vector machine classification boundary. The green circles are good instances, the red crosses are bad instances. And so what the adversary is trying to do is to push the red crosses more towards the green circles. So because this is a support vector machine boundary. So with all our mathematical computations, what we are trying to do is to move the adversarial, the support vector machine boundary to this, from the dash line to the blue line. The blue line is the adversarial support vector machine classification boundary. And now that we have moved, you can see that more of the red crosses, right, are being caught as bad instances. Otherwise, all of this would have been good instances, right? So they are being caught. So you can ask the question, why not move the blue line right here? Then all of the green instances will show as bad instances, right? And so we don't want false positives. We don't want false negatives. We want just right? So false positives is bad and false negatives is bad, right? So that's one example of adversarial support vector machine. Since then, there have been we were one of the early researchers, I believe, funded by the Army. Since then, there's been a lot of work on adversarial decision trees, adversarial deep learning, neural networks, and so on. Okay, so now, what about trustworthy machine learning AI analytics, right? So computations over big data may require massive computational resources, and organizations may use third party to outsource some of the computations. So whenever third party survey is used, computation data inherently becomes available in untrusted environments. There could be man in the middle attack during data transmission or insider threat from adversaries at third party location where computation is performed. We are conducting research on using Intel's secure encrypted data processing for secure encrypted data processing and trustworthy analytics using advancements in embedded hardware, such as Intel's SGX to support trusted execution environments. So that's one aspect. Another aspect that people are talking about now is applying formal methods, formal specification and verification, coming up with special logics for machine learning, right? Including logics for specification for deep learning and the verification of the machine learning algorithms, right? So that's another avenue of research. So, and the whole idea for us is to be coming up with verification, specification and verification so that some potential problems could be caught, right? Malicious code we could detect malicious code during the verification process. So coming back to the Intel chip, right? So trustworthy analytics, SGX enabled data analytics platform. And so this is all sort of in the chip, we have the application memory, runtime library, wrappers, and encrypted code. So the whole idea is to carry out the machine learning in the secure locations, right? Trusted regions. So the SGX enclave memory. And so you do the storage and executions. So there are various things for the Intel SGX, like global attestation and local attestation and so on. So I'm not going to discuss all of it, but just to the main point here is that there are special locations, trustworthy locations to execute the machine learning algorithms. Okay, so that finishes now part 1. Part 2, I'm looking at a particular application, and that's sort of IoT, in particular, Internet of Transportation and critical infrastructures, and looking at security and privacy. So we know that Internet of Things, right? So here, look at this, right? So our computers connected to televisions, connected to our Amazon shopping, connected to our coffee makers and tea makers and our cell phones and our refrigerators and our alarm clocks and our Wi-Fi and so on. That's Internet of Things. Similarly, you can have Internet of Transportation. All the cars are connected to the trains, and the trucks are connected to the roadworks. The whole idea is to everybody talking to each other, perhaps even applying AI techniques to make it easy for the drivers and for the transportation, right? So that's the whole goal. And the Internet of Things has major implications in transportation. Autonomous vehicles, AVs, aim at improving day-to-day activities, such as delivering packages, improving traffic, and the transportations of goods. And in the US, trucks alone carry estimated 63.3% of freight of goods. AVs are not limited to ground vehicles, but also include aerial and sea vehicles with a wide range of applications. Levels of automation for AVs range from 0 to 5, right? Current ground vehicles, automation is a bit low. It's at level 2. And aerial vehicles like drones and airplanes, level 4, fairly high. Companies are invested heavily. GM spent $728 million R&D in 2018, and they went up to 1 billion in 2019. I haven't seen the 2020 numbers, right? So while there's great potential in AVs and the improvements it can do to the transportation industry, security and privacy concerns pose new challenges that need to be addressed as we move forward. Okay, so security of autonomous vehicles. AVs evaluate their environment using a variety of sensors: camera, GPS, inertial measurement units, LiDAR, radar, and ultrasonic sensors. Previous research has shown sensors are susceptible to malicious tampering. Example, IMUs are susceptible to sound waves, and GPS receptors are susceptible to spoofing signals. So vehicles should verify the veracity of sensor signals before acting. But there are some challenges, right? So they're sensor-based. So AV relies on sensors to evaluate and interact with the environment. Inherited issues, as we said, sensors are susceptible to GPS spoofing and transduction attacks that manipulate environmental physical signals, visual, sound, magnetic, and need defenses. So classical computing security, such as memory protection, cryptography, and authentication, does not protect against these types of attacks. And to no verification, right? So due to real-time constraints, AVs trust and act upon sensor data without any form of verification. So there are many challenges because this is not network traffic. Network traffic is different from sensors, right? So these are a lot of challenges, and as a result, right, security could be compromised. So what did we do? So there could be attacks. So we built a physics-based anomaly detector, right? So build a reference monitor using PBAD, physics-based anomaly detection, for ground and aerial vehicles. So the algorithm has 3 parts. We build a model offline for AVs based on AV's physical invariance, and then we implement an online tool to monitor expected and observed behavior to detect the anomalies. And then, of course, raise an alarm. So online verification, raise an alarm if there's a significant residual difference between executions, right? So 3 parts. And so more details, right? Detailed design. So you can say, okay, so it looks very familiar, right? So you build a model, you do the verification, and then if it sort of deviates, then you raise an alarm. But we have to model the physical properties, that is a challenge. So my colleague, Professor Alvaro Cardenas, he's a control systems expert and cyber physical systems security expert. So he built the model with the student. The AV's invariants are calculated using it well-known nonlinear models for aerial and ground vehicles. So you can see this is the model: K state, YK input sensor measurements, pronounced Y tilde, right? So pre-processed sensor reading, commands to rotators, X is predicted states, LX, LY, LZ moments of inertia, needed for nonlinear equations. M is mass, D is drag factor, B is thrust factor. So you build these models. The AV's invariants are calculated using a well-known linear model for aerial, nonlinear model for aerial and ground vehicles, accelerometer, gyroscope, and magnetometer sensor data on X, Y, and Z axis for aerial vehicle, and vehicle positioning and steering angle is used for ground vehicles. So online stage, it's it's what control systems engineers have been using, Kalman filters, where the extended Kalman filter, EKF, is used to predict AV's physical behavior. So we didn't use any fancy AI techniques. Extended Kalman filter by estimating unknown parameters from noisy sensor input. The algorithm is divided into two sections that predicts and corrects the estimation before it is compared against the sensor data. So anomaly detection, a CUSUM algorithm, is a statistical algorithm, is used to then detect persistent attacks. It's already existing in the literature. And the alarm is raised if the residual difference is larger than a predefined threshold, right? So this was, physics-based anomaly detection algorithm. And how did we implement it? For aerial autonomous vehicles, we used Intel Ready-to-Fly drones, right? Controller PX4 flight controller focused on detecting GPS spoofing and gyroscope attacks. GPS attacks are detected after 0.2 seconds, while gyroscope attacks are detected after 1.5 seconds. And the overhead is about 5.43%. For the ground vehicles, you can see here, we built on top of Traxi Ford Fiesta Rally Chusek. Controller is ROS Kineticam, focused on detecting visual attacks on the camera. Attacks detected after 0.1 second. Overhead introduced was about 2.25%. Each threshold produces a probability of false alarms of approximately 2%. Okay, so that was the security. But of course, privacy. We haven't done really anything on privacy. But that's really important. Beyond the security of individual vehicles, the transportation sector could greatly benefit from a supporting infrastructure that allows communication between vehicles, motion sensors on lampposts, and surveillance cameras to help identify traffic jams, reroute vehicles, and increase vehicle safety. So from the user's perspective, there are privacy concerns, right? Because let's say I'm smoking in my car. Whether I'm supposed to smoke, I don't think so. But then I don't want people to take photographs and send information about me to my insurance company. Of course, I do not smoke. Or if I drink and drive, right? And we don't want that. So, and this could lead to privacy problems. On the one hand, AI is being applied for all of these applications. Without a doubt, AI machine learning is very critical for transportation. But then, for one thing, these techniques could be attacked, but again, this could also cause privacy problems, right? You can put collections of information together and infer that is something highly private, like driving patterns and so on. So legislatures, engineers, scientists should keep privacy concerns in mind as advances in IoT become more prominent in day-to-day activities. This will aid at improving the public perception, reduce hesitation from customers, and increase the adoption rate of new technologies. Okay. So now we finished part 2. Now part 3, so part 2 is real, we finished, and part 1, a lot of the information there, right? The projects we have completed. Part 3 is applying part 1 to part 2, applications of SecAI for Internet of Transportation and infrastructures. If we look at the time. Okay, so the Internet of Transportation systems are being attacked, right? So we know that. They are subject to attack like any other cyber physical system, right? So streaming data is being collected from such systems, including autonomous, and in the future, we are also going to have driverless vehicles. As transportation systems go electric, we need energy conservation, right? So threats to the security of such systems could cause massive damage, including accidents, loss of lives, as well as stranded on lonely highways due to attacks on energy management. So data science, machine learning being applied to analyze the data. Without a doubt, data science and machine learning are critical for Internet of Transportation. So can stream analytics learning being applied to, say, financial data and telecom data be applied to transportation data, right? So we know that data science is being applied for cybersecurity applications. So can these data science techniques be applied, for transportation security? So instead of Kalman filter, right, to detect the security attacks, can we use machine learning? The main question is to understand the nature of the complex transportation data, a lot of sensor data. These are not network traffic data, and adapt the stream analytics techniques and apply them to the massive amounts of heterogeneous sensor data being collected. Okay, so data science for transportation. Now, remember I talked about what happens if the machine learning techniques are being attacked. So machine learning is being applied, as I said, for a number of transportation applications to coordinate all the traffic, for the cars to talk to each other, for the trucks to communicate, cars to talk to the trains and keep order, right? Find the best driving routes and congestion control. So without a doubt, machine learning is crucial. Internet of Transportation systems will depend heavily on data science machine learning techniques for transportation of various for various applications, including optimum directions, driving without human in the loop, and so on. The adversary will be learning the models, right? The models that we are using, right, used by the vehicles, as well as learn about the data used in the training of the models. Imagine if the adversary attacks the transportation systems or aircraft, right? It could crash, right? Aerial systems. So adversary will attempt to thwart the vehicle's learning process. Therefore, the learning algorithms have to adapt to thwart the adversary sections. Eventually, it becomes game playing between adversary and the vehicle's machine learning algorithms. So what are the challenges? What sort of game will be played? Is it zero-sum game, Bayesian game, Stackelberg game? A lot of the researchers are using Stackelberg game. Need to understand the data. That is crucial. And research is only beginning on this topic, right? Adversarial machine learning for transportation systems. So what happens if these machine learning techniques are attacked? Remember, I talked about policy-based, privacy-aware, right, data management framework. But now, instead of a smartphone, we now have a vehicle, either aerial or land vehicle. And instead of healthcare data, social media data, and so on coming in, we've got radar data, GPS data, cameras, LIDAR, ultrasonic sensors. And so we do data collection, data storage, data analytics, data sharing. And we have a privacy-aware, policy-based autonomous vehicle. And some of the data encrypted and stored in the cloud, and we can access them through cloud-based services, sometimes anonymized data. So we haven't developed it. So what I'm saying, my point here is, can we develop such a system, right? Policy-based, privacy-aware data management framework for data collection, storage, analytics, sharing, access, analytics and sharing. And so this gadget here has to be somewhere inside the car. So that's the plan. And so what we are saying is, if policies are guiding the data collection, right? So remember, back in the social media application, policies will have to say, right, if you want to collect information about a person's COVID-19 or illness, the person has to say, yes, you can collect this data and share this data. So if there's data about me, I've got to give permission. So data cannot be collected without the permission, say, of the data about the person about whom data is being collected. So similarly, we need to come up with appropriate policies. And then my last chart, I think I'm a little bit early because usually, right, when you have recorded presentation and there are no sort of questions at the time. So, I was supposed to, this is like 1 hour, and I think I've taken about probably around 45 minutes. But that's okay. I'll be there to give this presentation live if needed, and I'll be there to answer questions. So, summary and directions. Developments in integrating cybersecurity and AI data mining exploding. Without a doubt, cybersecurity, machine learning being applied for cybersecurity applications like insider threat And these machine learning techniques could be attacked, right? Applications of AI for insider threat and security for AI, right? These AI techniques could be attacked. So when we talk about AI, we mainly mean focus on machine learning and deep learning, but of course, other aspects of AI like knowledge representation, knowledge graphs could be attacked, or planning systems could be attacked. Also, developments in privacy-aware healthcare, managing one's life's activities, right? Privacy-aware quantified self. At the same time, with the development of Internet of Things, including Internet of Transportation systems and infrastructures, security and privacy solutions are being developed, but they are mainly physics-based solutions. As driverless cars become a reality, more and more of the AVs will use AI machine learning techniques, right? How can we develop AI solutions for detecting malware in autonomous vehicles? And how can adversarial machine learning work in the autonomous vehicle systems? Well, these are some questions. Can we develop a privacy-aware policy-based data management framework for Internet of Transportation and infrastructures? Is it possible to perform trustworthy machine learning analytics efficiently when so much of data is coming from all directions, right? So can we develop trustworthy machine learning? And what about the formal verification systems, right? Formal verification, specification and verification. That's really important these days for machine learning, right? Because more and more machine learning, so it'll be good to detect those malicious codes. And so numerous opportunities exist for substantial research. Research is just beginning, right? So what I have mentioned here, we could have probably about even some of the data mining or machine learning for cybersecurity, one, and adversarial machine learning, and then privacy aware policy based and security and privacy for transportation systems. And then we could have applying AI. So like at least 8 PhD thesis worth of work. And I provided it at a fairly high level, the information. And as I said, here's all our contact information, myself, Professor Cardenas, Professor Kantajalu, Professor Latifa Khan, Dr. Raul Cunanes, and Ms. Rhonda Walls. Okay, so this sort of ends my presentation. So I'm going to stop sharing. And again, my closing words, just a second. So my closing words here is that without a doubt, as I said, right, artificial intelligence and machine learning, it's sort of everywhere. And cybersecurity is also everywhere. Anytime you have a microprocessor in any type of system, that system could be attacked. Whether it be your smartphone or your computer or your laptop or your television with some microprocessor, or your pacemaker, or your other healthcare gadgets that you carry around, your refrigerator, you name it. And so if these systems are being attacked, right, AI techniques are machine learning is being applied to detecting and perhaps even preventing these attacks. Because if you know what these attacks are, perhaps you can do some analysis and say, oh, these attacks are some of the future attacks and you could prevent them. So that's one thing. And the other is that the machine learning techniques themselves could be attacked. And then the third thing is that the privacy-aware quantified self, right? That's another problem. So what we are saying is policies govern everything. And then in part 2, we talked about security and privacy for transportation systems. And then our algorithm was, we used extended Kalman filter. Then I also briefly talked about privacy for secure privacy for Internet of Transportation systems. And then part 3 was applying part 1 to part 2. That is, when you bring AI into the picture, how can machine learning AI be used for detecting attacks in transportation systems? And second, what happens? Adversarial machine learning, right? Machine learning techniques for transportation systems could be attacked. And the third is, what about privacy for transportation systems? Can we develop a policy-based, privacy-aware data management framework for Internet of Transportation systems? And then I also talked about trustworthy machine learning using SGX chips and verification of, formal verification of of systems, of the machine learning algorithms, can we apply that to transportation systems? Okay, so I think, I've talked for about, around 47, 48 minutes, I believe. And so, as I said, I will be there at the meeting, at the conference, hopefully to answer questions. And again, thank you very much for listening to the presentation. Thank you.